In this lesson, we're going to cover the scary topic of helical interpolation. It's often a much misunderstood subject, and it's not as difficult as it seems when it's broken down step by step, which is exactly what I'm going to do now. But first, let's have a look at the different things that it can be used for. Generating holes. Sometimes we need to produce a large hole, bigger than we wish to use a drill for, or maybe a flat bottom hole. The easiest way to do this would be to generate it with a milling cutter rather than using a drill. And that's what this part of the course is about. I'm going to show you how to generate a hole using helical interpolation. We can also use it for circular ramping. This is where we cut down to depth to machine a feature such as a pocket or a slot, or we can even use it to start off cutting a profile to bring the cutter down to depth. And finally, my favourite, thread milling. This is where we can cut a thread by milling down in a spiral using a thread mill. This is great for producing threads in very hard materials such as titanium. So what exactly is helical interpolation? Let's have a look. Using a milling cutter, we can make a pocket, like the one shown in this diagram, by cutting in a radial move, but also in the Z-axis at the same time. So we're using GO2 or GO3, whilst also coming down in Z, in a spiral shape. This also explains why it's often called spiral milling. To ensure we don't leave a pip or a raised part in the bottom of the flat hole, we need to use a cutter that is larger than the radius of the hole, as shown here. Now let's have a look how we can use helical interpolation to mill a 60mm bore inside a component. As a way to make the program easy to follow and clear to understand, I've chosen to put the datum position where we wrap it in our milling cutter. This makes the code look a lot cleaner and easier to follow, so you're not just reading a bunch of numbers and not understanding what everything does. Since we're going to be machining a 60mm bore, I'm going to be using a 40mm milling cutter for this operation. That way we don't leave a pip in the middle of the blind hole, because the milling cutter is over half the size of the diameter of the bore. It's larger than the radius. The code T06 designates our tool number. We're using tool 6, and the following digits 06 is our offset number, so T0606 is tool 6 offset 6. And an operator's note in brackets that tells the operator which cutter to load into the spindle for this operation. MO6 is our automated tool change code. This tells the machine to pull the tool number 6 from the carousel and load it into the spindle. I've added a few more G codes to our safety line, so let's go over them. The G90 tells the machine we're using an absolute measuring system and not incremental. G54 is our datum. This calls information from the machine controls into the program to tell it what datum we are using and where it is. G21 tells the machine we're using a metric system. G17 defines the plane that we are working on. G80 cancels any cycles that may be active. If we stop the machine halfway through a section of program where there's a cycle active, this will cancel it when it reads this line. And finally G43, which is our cutter compensation. Calling upon a G43 with no offsets tells the machine to look into the tool table and pull the offsets from the tool table from offset 6, tool 6. The S value defines our spindle speed, and MO3 turns the cutter on in a clockwise direction. Now we wrap it to our start point, or our datum position, which, as I explained just now, I've set to X0, Y0 at the start of where we wish to cut, just to make the program cleaner to read. On a separate line, I rapid the cutter down to Z 1mm. This brings it to 1mm of the surface of the material. MO8 turns on our coolant. At this point, you will know if you set your tool correctly, because rapiding 1mm off the face of the material won't end well if you haven't. Switching over to a GO1 feed rate command, I now bring the cutter down to 0.1mm of the faceling material, using a feed rate of 200mm per minute. Now we can start cutting in a spiral fashion. Our GO3 tells the machine to start cutting in an anti-clockwise direction, whilst our X movement is the end of an arc, which is the opposite side of the bore. We keep Y as 0 because we don't wish to change that. We're coming down in Z 2mm during this procedure, with a radius of 30mm to cut a diameter of 60mm. I've not added a feed rate as it's still active from the line above, but if we wish to use a different feed rate while we're circling interpolation like this, we can do. We now move the cutter back to X0, Y0, the beginning of our circle. Our Z minus 4mm takes a 2mm cut during a semicircle. The radius remains the same throughout. Now we have machined our first complete spiral in a circle. We now just repeat the same blocks of code by bringing it down in Z each time by 2mm. If I set the datum in a different position, we wouldn't be seeing simple numbers to read like X 60, Y 0. This is why I've done this, purely for clarity for the demonstration purposes of this video. I am milling this circular pocket 10mm deep, so on this line it takes us to our final depth of 10mm. Without indexing down in Z anymore, I'm now taking one last circular pass to clean up the bottom face of the bore. We can also increase the radius here to clean up the sidewalls, but that would mean cutting the rest of the bore undersized slightly. On this block we complete our final circular motion. As I rapid out our bore, I do so at an angle. Bringing it into Z30 brings the cutter into the centre of our bore as we come out. This is because I don't wish the cutter to touch the side or the bottom of the bore on its way out the job. Now that we are free from the component, I can wrap it away in Z safely. This is also a good time to turn off the coolant. For that we use MO9. One way to tell the machine to go back to its reference position is by using G53, the machine datum. We can also use G28 to get the machine to go back to its reference point. MO5 stops the cutter. G40 turns off our cutter compensation. And finally MO1. This is our M code for optional stop. If the operator wishes, he can push a button on the controls and have the machine stop at this point so we can measure the bore to make sure it's correct. And that is how we use helicoil interpolation on a milling machine. It has many uses and it's worth experimenting with and practicing with. It's a handy technique to know, and you will find you use it quite a lot when programming CNC milling machines.